In this video, we're going to look at what happens to delta H when we take an exothermic reaction like this one and flip it around to make an endothermic reaction. So once again, this reaction was the same one that was used in the previous video with the balancing now fixed. For those that don't recognize it, this reaction is what we call the cellular respiration reaction, which is the chemical reaction in which glucose is broken down in the presence of oxygen in order to produce a fairly large amount of energy, which means that we are dealing with an exothermic reaction here. And even if we didn't know what this reaction was or what it was for, we can see that the delta H energy term is listed as a product here, meaning if we actually want to write out the proper number with the correct sign, because this is an exothermic reaction, our delta H value is going to be negative 2,880 kilojoules per mole. Now, if we want to draw the graph, we can remember the formula for delta H of the potential energy of our products, subtract the potential energy of our reactants. And because delta H is negative, that must mean that the magnitude of the potential energy of our products must be smaller than the potential energy of our reactants, which we can write out on this graph like this. Next, we need to connect these with the characteristic arch that we see in potential energy curves. And finally, we can label the axes, the y-axis with potential energy in kilojoules and the x-axis with time. Now, if we actually wanted to show where delta H can be visible on the graph, again, we take the potential energy of our products and subtract from that the potential energy of our reactants, and this difference here allows us to find where delta H is simply by looking at this graph. For those that are wondering whether this can also apply to endothermic reactions, the best way to find this out would be to actually try to do this with an endothermic reaction. So what we see here is exactly the same reaction, the cellular respiration reaction, but the old reactants in cellular respiration are now the products here, and the products in cellular respiration are now the reactants. And look at that, I need to fix the same balancing mistake. Now again, biology students will recognize when you take cellular respiration and flip it around, the opposite reaction of cellular respiration is of course photosynthesis, in which plants take energy that they receive from the sun and use it to produce sugar that they in turn break down for their own energy. Now, because sunlight is going into this reaction and is used to combine water and carbon dioxide to make sugar, we know that energy is a reactant here, which means we're dealing with an endothermic reaction. Now, again, even if you don't know what this reaction is, we can still identify that this reaction is endothermic because we see that our energy term is a reactant instead, meaning that if we were to write out delta H independently of the reaction, it would be positive 2,880 kilojoules per mole. Likewise, if we were to draw this out, we know from the formula of delta H of being potential energy of products minus potential energy of our reactants, if our delta H value is positive, that must mean that our products must have a higher potential energy than our reactants do, and we can complete the graph by filling in the characteristic arch like this, and we can put in our variables, potential energy in kilojoules on the y-axis, and some variable of time in the x-axis like so. Now, what we can see if we actually were to draw this graph out using a computer or something more accurate and precise than my pen here, we could see that these graphs come out as being mirror images of each other. And if we remember the delta H value in both equations, the delta H value of cellular respiration was negative 2,880 kilojoules per mole, which mirrors the delta H of photosynthesis exactly, which is positive 2,880 kilojoules per mole. And this makes sense. The magnitude, because cellular respiration and photosynthesis are the same reaction, but simply looked at from a different starting point, it makes sense that the magnitude of each of these delta H numbers is exactly the same, because you're dealing with the same compounds, just in a different order. However, the only thing that changes is the sign, is the direction. So this is one easy shortcut that you can remember, is if you take an exothermic reaction and flip that reaction around, the difference in potential energy between reactants and products remains the same, only because the reaction is going in the opposite direction, the sign flips for them. In the next video, which will be the longest in the series, we are going to examine this distance here between the reactants and the beginning of our reaction, and the point at which potential energy is the highest on the graph, and explain why the potential energy curves feature this characteristic arch in the center.